Yes, now we can start.
Okay, today I would like to tell you about some new results for Kuramoto model. Especially, I will speak about information geometry in Kuramoto model, and the outline of my talk is following. This talk is based on our recent paper with Alexander Gorsky, and also I will use some facts from the book by Amari. This book is about information geometry and its applications in different fields of science. So first of all, I would like to speak about some basics of information geometry, and I will introduce some needed concepts. And then I will present a brief discussion how we can apply information geometry for phase transitions. I will speak about classical phase transitions and quantum phase transitions. And at the end of my talk, I will present our result for Kuramoto model, and I will show that information geometry plays an important role in Kuramoto model. So the first part of my talk is based on these two books. Both books are devoted to information geometry, and they provide all needed ideas and concepts for everyone who is interested in information geometry. So you can just read this book and obtain some new information about this field of science. We start from the very simple object. We start from the probability distribution. It is the function p. Here, the x is the vector of random variables, and xi is the vector of parameters. Of course, this probability distribution function is normalized to unity. And the first statement is that all probability distributions, when we vary the parameter xi, forms so-called statistical manifold. So the manifold M is constructed from probability measures for every possible value of parameter xi. And the first reasonable question is how to measure the difference between two probability measures. How I can differ the probability distribution P1, which corresponds to the parameter value xi1, from the probability distribution P2 with parameter xi2. And the answers for this question is just consider so-called divergence function. And the divergence function is the function. It is a definition of divergence function. Let 2 points P and Q are points on the manifold M, and their coordinates are xi P and xi Q. So the function D is called divergence if it satisfies the following conditions. First of all, the function D is positive, and it can be equal to 0 if and only if P is equals to Q. And if my points P and Q are close enough, I can expand the divergence function into the Taylor series, and the divergence function has the following Taylor series expansion. So you can see that this is a metric of my manifold, and this is the expansion of divergence functions for two close enough points. And in general, of course, the divergence function can be non-symmetric. So if I interchange 2 points, in general, I can obtain a different value of divergence function. The common examples of divergences are Kullback-Leibler divergence, fidelity, Jensen-Shannon divergence, and etc. The divergence function is a well-known object in quantum computing community. In quantum computing, in quantum computing community, all people knows about divergence, and they usually use fidelity to describe how two quantum states differ from each other. And next, I would like to present a definition of so-called standard F divergence. The standard F divergence is defined as follows. it was defined in 1967. And here the f is a convex function, convex differentiable function, which satisfies these conditions. And there is a theorem that guarantees that any standard f divergence gives the same Riemannian metric, which is called Fisher metric. So this is a definition of Fisher metric. And there is a theorem that guarantees that any standard f divergence rises the same Riemann metric. It is a very important point. And also there is a theorem that guarantees that invariant tensors derived from any standard f divergence are given by these expressions. The very first formula is a Fisher metric, and the second formula corresponds to three indices object, and I will define it further. And alpha is a parameter that rises from the function f. Is everything clear? Can we proceed further?
Sorry, can you say it again? What is capital E?
Capital E?
Yes,
T?
E. No, E. It's some probability average. What is it? What is E?
You mean the second formula on this slide?
Yes, yes.
It is logarithm. It is logarithm function.
I mean the bolt.
Okay. So we just compute the average with respect to probability measure P. It is the integral over x of this guy with additional P of x.
How it is called? Could you remind how it is called in probability language? Is it very?
Is it simply? It is the simple average.
It's just average.
Yes.
So
the next definition that I needed is the so-called Levi-Civita connection. It is defined by Riemann metric, and for statistical manifold, I can introduce two connections. I can introduce dual connections, gamma and gamma star, and then I can define three indices object T. It is a tensor, and introducing all these guys, I can define so-called alpha connections. And the alpha connections are defined by these formulas. And existence of alpha connections is a crucial property of statistical manifolds, because in usual Riemannian geometry, as I understand, we do not interested in such connections, and as I understand, alpha connections appear only for statistical manifolds. So it is a feature of probabilities, or it is a feature of manifolds that formed by probability measures.
Yeah. So the index F here is kind of, you don't need this index.
I just on this slide the index F is denoted as Fisher, and I would like to keep this denotation because in general, the tensor T that corresponds for a specific F divergence, it is different from. Okay, just a second. In general, for a specific F divergence function, the three index tensor T is different from the tensor that I denoted by TF. Let me proceed further, and you will understand the difference between these two tensors.
Yeah, just naive notation. So the tensor on the line before, it doesn't have this index, so it's not a mistake. I mean, these are just two different tensors.
Yes, they are two different tensors, and they are related to each other by the multiplier alpha. And the last definition that I needed is so-called alpha flat manifold. When I introduce alpha connections, I can also introduce alpha curvature tensor. And then if my statistical manifold has identically zero alpha curvature tensor, I say that my statistical manifold is alpha flat. I can reformulate this definition in the following way. If there is an alpha, that is not equal to zero, and alpha curvature tensor identically zero, so my statistical manifold is alpha flat. And the simplest possible example is the statistical manifold, which is formed by Gaussian distributions. It is simply Gaussian distribution with average mu and dispersion sigma. And the statistical manifold, which is formed by these Gaussian distributions, is alpha flat for alpha equal to plus minus 1. And the more complicated example is a statistical manifold of Cauchy distributions. And one can check that statistical manifold of Cauchy distributions is not alpha flat.
Sorry, and the metric for Gaussian distribution is what? It's just flat metric, or?
One can compute it. It's quite easy to compute, and the metric is the metric seems like a DS2 metric. It is the metric of two-dimensional hyperbolic space.
Yeah, but then but in 2 dimensions, so it's just 2-dimensional. But in 2 dimensions,
yes, we have 2 parameters. We have the parameter sigma and parameter mu, and it is 2-dimensional hyperbolic space.
Yeah. In 2 dimensions, any torsion is trivial in a sense. I mean, but yes, but ADS is not flat. Oh, okay, interesting.
Yes, it is a feature of statistical manifold. It is for Gaussian distribution, we can say that Gaussian distribution manifold is alpha flat, but for Cauchy distribution, it is not true.
I'm just trying to understand what is this connection. So you're saying that there is a special connection on.
I should compute the Levi-Civita connection gamma 0. And then I compute.
This one is not flat, of course. I mean, Riemann tensor is not 0 for ADS2. ADS2 is not flat space.
Yes.
But the torsion is some special. Should be some special torsion. The tensor T is called torsion, and it should be very special. Well, probably if you go ahead.
I can provide calculations if you're interested, but after the talk, okay?
Okay.
And the final note is devoted to so-called Bregman divergence. There is a specific class of divergence functions which is called Bregman divergence, and here you can see the definition of Bregman divergence. So if I can write down the divergence function between 2 probability measures in the following way, where the psi is a convex function, this divergence is called Bregman divergence. And for Bregman divergence, the Fission metric is simply given by derivatives of psi function, and skewness tensor, the tensor T, is given by and the 3 indices tensor T is also given by simple differentiation of convex function psi. And finally, the statistical manifold is the triplet of M, which is manifold, G, it is Fission, it is metric, and T, it is skewness tensor. And for any standard F divergence, the metric T, the metric G is equal to Fission metric, and the skewness tensor T can be expressed via the tensor TF. It is the last formula on this slide. For any standard F divergence, the metric of statistical manifold coincides with Fission metric, and skewness tensor is given by the following formula. Okay, it is the final note about information geometry, and I hope that you have developed some intuition about manifold of probability measures. And the next part of my talk is devoted to application of information geometry for phase transition. And the first this slide is devoted to very brief description of how we can apply information geometry for classical phase transitions. There are several papers that deals with classical phase transitions, and most of these papers are devoted to gas-liquid transition. Some of papers are devoted to liquid-liquid transition, and if you're interested, I can provide all the reference, and you can just read some of these papers. And the key points are following. The scalar curvature of statistical manifold is related to correlation lengths. And I hope that you understand how the statistical manifolds appears in classical phase transitions, because when you describe the statistical, when you study a system, you always deals with partition function, and you can always provide the probability measure, because of course partition function is closely related to probability measures. Is it clear, or it should be, is it clear or not?
It is clear. Yeah, I have a question. Is there any relation of that metric to what is called the Molodchikov metric? Or it's, I mean, in that setup, what is completely different story? I'm just trying to...
To be honest, I don't know.
Actually, they are relatives, but not identical. So,
but at least these both are the metrics on the same space, on the space of parameters of our...
Exactly. So both of them are the metrics on the space of parameters, but you consider different objects. We consider derivative of different objects.
And the crucial fact about classical phase transitions that in most of systems we always deal with exponential family. So the probability measure can be represented as follows. It is simply the exponential of some function, and there is a multiplier q of x. And the main statement is that we can always parameterize our probability distribution for classical phase transition as exponential, is a member of exponential family. It is very important fact. And we can always construct the function psi that is simply the thermodynamic potential, and so the statistical manifolds of probability distributions for classical phase transitions are quite simple. In some sense, they are quite simple.
Sorry, what is theta?
Can you repeat?
Theta, the variable theta, what is that?
The variable theta corresponds to the vector of parameters. It is some parameters of our system. And h is a function, is some function of x.
And how these parameters are defined?
I can provide some examples. On this slide, you can see the scalar curvature for two-dimensional Ising model. And here you can see two parameters. The couplings, the spin-spin interactions in different directions. So in such case, I can say that my variable theta is a set of two variables. My variable theta corresponds to the coupling constant G and K. If you consider the Ising model, if you consider one-dimensional Ising model in transverse field, you can find that theta as a vector of parameters corresponds to the external magnetic field and spin-spin coupling. Is it clear?
Yes, thank you.
Okay, and on this slide, you can see the picture that represents the scalar curvature for statistical manifold that corresponds to two-dimensional anisotropic Ising model. And you can see that the scalar curvature diverges at the point of phase transition. So the main statement is that scalar curvature, or maybe a Fission metric, are sensitive to phase transition point. And is it true? It is true for classical phase transitions. It was illustrated in several papers, and it seems that this fact is well known. And the second story is about quantum phase transitions. And in quantum phase transitions, the situation is slightly different because in quantum phase transitions, we deal with a wave function instead of probability measure, which corresponds to wave function squared. We deal with wave function. And the first, what we should do is to consider two infinitesimally separated states in parameter space. And the psi is a wave function and q is the set of parameters, and we can construct the following object. But however, the object alpha is not gauge invariant, and it was shown by Provost that true object is so-called quantum metric, and it contains real part and imaginary part. And it was shown that the imaginary part corresponds to BE connection. So this object is very nice. It is gauge invariant and so on. And as in classical phase transitions, it was shown that critical points in quantum systems, so we speak about quantum phase transitions, critical points are visible from peculiarities of quantum metric and peculiarities of scalar curvature. There are a lot of papers by Anatoly Polkovnikov, by Zanardi, and etc. And in all these papers, authors consider spin chains and different spin chains and some other systems. And this construction can be generalized for density metrics, and it was done by Johan Erdmenger, and you can find that. So the statement for quantum phase transitions is the same as for classical phase transitions. We can see critical points from the peculiarities of quantum metric or peculiarities of scalar curvature. And on this slide, you can see the scalar curvature for statistical manifold that corresponds to quantum XY chain. So we have XY chain with two parameters. Gamma is a spin-spin interaction, and H is the external magnetic field. And here you can see the plot of scalar curvature for this chain. You can see that at the critical point, the scalar curvature is divergent. On this slide, you can see the quantum metric and the scalar curvature for more complicated model. It is called LMG model. It is Lipkin-Mishkov-Glick model. It is very similar to XY chain with all-to-all coupling. So we consider the simple XY chain, but all spins coupled to each other. And the main point is that this blue line corresponds to the phase transition to the critical line. And the main point is that you can capture the quantum phase transition from the analysis of quantum metric and the scalar curvature. So I'm sorry because I forgot about the scalar curvature. And this slide you can see simply the plots of quantum metric for Lipkin-Mishkov-Glick model. And here omega and psi are some parameters of this model. Okay. So I told about information geometry, I told about classical phase transitions and quantum phase transitions and how we can capture it by information geometry. And this is the main part of my talk. I will speak about information geometry in Kuramoto model. The equations of motion for Kuramoto model are given at the very first formula on this slide. It is non-Hamiltonian system. Here, omega is the oscillator eigenfrequency, lambda is the coupling between oscillators, and here we have the set of n coupled to each other oscillators, and they interact by sine function. And we can introduce a synchronization measure, which is order parameter for this model, and the order parameter is given by, the order parameter is simply average complex phase. So this order parameter have imaginary part and real part. And I can rewrite the equations of motion by introducing the complex phase variable. I introduce the variable z, and then I can perform Möbius transformation. It is a very long story why I apply the Möbius transformation, but the important fact that this model has integrals of motion. It is not integrable, but it has integrals of motion. And the existence of these integrals of motion causes the low-dimensional dynamics. And I can represent the dynamics of Kuramoto model by acting of Möbius transformation. I have a Möbius transformation which parameters depend on time, and I act this Möbius transformation on my initial conditions. Here, the Z0 is the initial condition of my model. So at 0 time, I have a set of points on the unit circle, and evolving in time, I just rotate my points on the unit circle by the Möbius transformation. And if I substitute the complex phase into equations of motion and then apply Möbius transformation, I can find the low-dimensional dynamics of Kuramoto model. It was done in it was done in 2009. It was done several years ago, and the result is following. So I can find, instead of considering dynamics of n particles, I can consider two equations. The Möbius transformation have two parameters. One is real parameter, it is zeta, and one is complex parameter, it is w. Instead of a set of n equations, I can write down two equations, one for complex variable and one for real variable. So I perform the dimensional reduction. And the resulting equation for W is given on this slide. It is the second formula. It is quite complicated equation because it is very nonlinear. It is not solvable, and and so on. And here the function P is so-called Poisson kernel. It is the Poisson kernel that naturally appears when one considers the solution of boundary problems in two-dimensional space. Okay, is it clear, or should I comment something?
Sasha Belborodov asking what is EOM. I think this
Equations of motion. Sorry,
it spells for equations of motion. Yeah. So you said there should be also equation for psi, but you didn't read.
To be honest, I can forget about this the zeta. You mean zeta, yes? The function zeta.
Yes, zeta, yes, not psi. Sorry.
Yes, I can forget about the function zeta. It is a it is not so interesting. It is not so interesting because if you substitute the expression, this expression for variable z into the expression for the parameter, and okay, I can just speculate. I can safely set that zeta is constant. And zeta is equal to 1. It is enough. It is a result of computation, but I don't want to go into derivations. Just forget it. And this equation for the function w is our object of interest. And just a second. On this slide, you can see the synchronization transition. So we start from the set of points on the unit circle, and during the evolution of time, all the points goes to one point that moves on the unit circle. It is synchronization transition. It is purely a phenomenon that is described by Kuramoto model. And in continuum limit, instead of a set of particles on the unit point, we have a distribution. We have a distribution F0. It is the initial distribution, and it evolves in time. So I can rewrite the equation for my function W as follows. Here you can see that I introduce the object, the function P, and this index WC denotes rapid Cauchy distribution. Let me return to this slide. One can notice that the Poisson kernel is tightly related to rapid Cauchy distribution. So if I integrate over Z, I obtain 2 pi. And if I introduce the normalized Poisson kernel, I obtain the rapid Cauchy distribution. You can see, you can think about it as follows. Instead of usual Cauchy distribution, where the random variable goes from -infinity to +infinity, you just compactify the random variable, and you consider that your random variable lives on the unit circle. It varies from 0 to 2 pi. Is it clear? And the equation for W becomes this, and here I integrate over the contour of length 2 pi, and we ask 2 questions. The first question is very natural, because it was shown previously that Kuramoto model dynamics is tightly related to gradient flow in hyperbolic space. And we ask, how does hyperbolic space appear? And the second question is how the integral is right-hand side of this equation. Is integral in right-hand side of this equation related to something like entropy? Because we have a quite interesting structure. It is very similar to entropy, and to informational entropy. And we would like to understand how the integral on right-hand side related to something like entropy, or maybe more interesting objects. And we have shown that the structure in right-hand side is clearly the Kullback-Leibler divergence. So just a second. The structure in the right-hand side for equation for W is simply Kullback-Leibler divergence. So it measures the difference between 2 probability measures. It measures it says how the initial distribution differs from the instant distribution on the unit circle. Let me return on this slide. Here, the function W is a function of time, and the object in right-hand side, the integral in right-hand side, is a Kullback-Leibler divergence. It measures how our instant distribution on the unit circle differs from the initial distribution. And in terms of Kullback-Leibler divergence, we can rewrite our equations of motion in this form. So we see that there is a gradient flow. We can show that is the gradient flow on hyperbolic space, and the object in right-hand side is a Kullback-Leibler divergence. And this structure is well known in information geometry community, because it was shown, it was discussed a lot of times. It was discussed a lot, and it was shown that gradient flows on statistical. The statement is that gradient flows on statistical manifolds are well known, but usually these gradient flows are considered for exponential family distribution. It was made by Nakamura and Fujiwara in 2000. And the Kullback-Leibler divergence is the Bregman divergence for exponential family distribution. It means that we can find the potential function psi, and we can rewrite the gradient flow on statistical manifold, which is formed by exponential distributions, in the following way. it is the gradient flow for it is the gradient flow on statistical manifold, which is formed by exponential distributions. Inspecting our gradient flow, we conclude that hyperbolic space, the apparent hyperbolic space, is the statistical manifold of rapid Cauchy distributions. But instead of potential function, we deal with Kullback-Leibler divergence. And the last statement is that synchronized state, which is correspond to W goes to 1, is characterized by peculiarity of Fisher metric. And if I compute the Kullback-Leibler divergence, I can see that Kullback-Leibler divergence blows up in the synchronized state. And there is an open question. Can we say something more about this gradient flow? And can we find an appropriate divergence function that gives the potential function psi? So the problem is following. We see that this equation corresponds to gradient flow on statistical manifold, but instead of derivative of some potential function, we have the derivative of Kullback-Leibler divergence, and it is in some sense it is a problem. But nevertheless, we have shown that synchronized state corresponds to peculiarity of Fisher metric, because
Artem,
I can.
Sorry, may I ask? I think I didn't catch. So, in what sense you have shown equation 4? So we have shown that it is related to Kullback-Leibler divergence.
Because it is purely Kullback-Leibler divergence. It is definition of Kullback-Leibler divergence.
But when you started, is it obvious that you should obtain this Kullback-Leibler divergence? Or?
Yes, in some sense it is obvious because this equation is known. But as I understand, no one have said that it is a Kullback-Leibler divergence. But
I see. So you're saying that you rewrite your original equations in terms of equation 3.
Yes.
Notice that 3 is nothing else but
Kullback-Leibler divergence.
Exactly.
Yes. And if I compute the Fisher metric for rapid Cauchy distribution, I can see that this Fisher metric corresponds to the metric of hyperbolic space, two-dimensional hyperbolic space. It corresponds to the Poincare disk. And
this distribution, Kullback, whatever, is it related to Keller potential, somehow to Keller potential of this metric? It seems like very closely related, no? Because it's kind of its gradient flow. It looks like, I mean, this derivative over omega W bar reminds me.
I know that this gradient flow is related to so-called Boseman function, but I don't know about Keller potential.
Okay.
Once again, it's very close to the Keller potential, but not identical.
So for simple Kuramoto model, we conclude that hyperbolic space appears as statistical manifold, and the statistical manifold is formed by rapid Cauchy distributions. And synchronized state corresponds to peculiarity of Fisher metric. But in some sense, this example is not so clear. The more appropriate example is so-called Kuramoto-Shakaguchi model. The equations of motion are quite simple. Here, they are almost similar, but we add a stochastic term. The stochastic term eta is nothing more than white noise. It has 0 time average and non-zero 2-time correlator, and d is the positive quantity, which is nothing more than noise amplitude. And it was shown that for Kuramoto-Sakaguchi model, this model exhibits continuous phase transition with respect to coupling constant, and the noise plays role of temperature. I can show that the continuum limit of this model is described by Fokker-Planck equation. It is quite simple derivation. And on this slide, you can see the phase transition in Kuramoto-Sakaguchi model. We plot the absolute value for the parameter, and we study how the absolute value for the parameter depends on ratio of coupling constant to noise. The horizontal axis corresponds to noise D. And at the critical point lambda c equals to D, there is a continuous phase transition. And I can show that synchronized state for Kuramoto-Sakaguchi model is described by stationary solutions of Fokker-Planck equation. So I have a set of equations of motion. I take the continuum limit, and the continuum limit is described by Fokker-Planck equation. And the stationary solution corresponds, and synchronized state corresponds to the stationary solution with non-zero value of R, and R is the order parameter. And the stationary solution is given by this expression. And I can find the self-consistency equation is quite simple, and I can find also the critical point. And the critical point is lambda critical is equals to D. And one can notice that
self-consistency.
Okay, let me comment it. When I find the stationary solution, I substitute the stationary solution. I substitute the stationary solution into the expression for the parameter. So let me return to this slide. Sorry for it. The order parameter in continuum limit, the order parameter is given by integration. The order parameter is given by integral over theta with my stationary distribution rho. Is it clear?
Yes.
So I substitute the stationary solution into the expression for the parameter and then integrate over theta. And then after this, I obtain the self-consistency equation. And I'm interested in non-trivial solutions. So I'm interested in non-zero values of the parameter, and I can see that non-zero values of the parameter corresponds to lambda is larger than lambda critical, and lambda critical is equals to D. And one can notice that stationary solution is nothing more than von Mises distribution. The von Mises distribution is the compact distribution. It is rapid distribution on the unit circle. It is well known in probability community, and we can capture the phase transition from the Fisher metric of von Mises distribution. So I find the stationary solution and I consider the Fisher metric for these stationary solutions. And on this slide, you can see the Fisher metric components as the functions of lambda over lambda critical. So there are two parameters. The first parameter corresponds to D, and the second parameter corresponds to lambda. So my metric is two-dimensional, and moreover, I can show that it's diagonal metric, and here I plot diagonal components of my Fisher metric. You can see that the first component exists only in synchronized state, and the second component is identically zero in non-synchronized state. So we can see the phase transition in Kuramoto-Sakaguchi model in terms of Fisher metric for stationary solutions of Fokker-Planck equation. It is a statement. Also, we can plot the metrics. We can plot the Fisher metric components as the functions of ratio of coupling constants for a given fixed value for the parameter. And you can see that in synchronized states, the behavior of Fisher metric components change. In the non-synchronized state, the first diagonal component of Fisher metric, the first component of Fisher metric decreases in synchronized state, whereas the second diagonal component of Fisher metric increases in synchronized state. So the statement is similar. We can see the phase transition for Kuramoto-Shakaguchi model in terms of information geometry, in terms of Fisher metric. And in summary, we have shown that Kuramoto model dynamics can be described as gradient flow on statistical manifold. And we have seen that synchronization corresponds to peculiarity of Fisher metric of such manifold. And the open questions and our further plans is devoted to find potential function for the rapid Cauchy distribution. And we try to say something about quantum version of Kuramoto model. And we hope that it is related to so-called Bohm-Madelung formulation of quantum mechanics. So it is the end of my talk. If you have any questions, I will try to answer them.
Okay, thank you. Please, your questions. So, I didn't understand that. How you basically compute the metric? So all the pictures you have shown, is it comes from numerics or how?
No, I can compute I can compute by hand.
Mm-hmm.
The very first expression on this slide is nothing more than probability distribution. It is simply a probability distribution that is normalized to unity. So I just pick this expression, and then I pick this expression, and then I compute Fisher metric by definition. So I take the logarithm, I perform differentiation with respect to my parameters, and then I perform integration over random variable.
Mm-hmm.
So I just pick the row 0, I compute logarithms, I compute derivatives, and they integrate over theta.
Mm-hmm.
And I obtain my components. They are function of lambda and d, and then I obtain the resulting plots.
Mm-hmm. And the hypothesis that the corresponding Riemann tensor is 0, is it confirmed or?
As I remember, I have seen that it is not 0, but actually I don't remember. To compute the Riemann and to compute the curvature tensor, the computation of curvature tensor is a little bit more complicated.
Mm-hmm.
I don't understand which manifold. I don't understand which manifold I have found, because the metric is quite non-trivial.
But you don't care about topology of this manifold. This is just local.
Yes,
thing, right?
I don't care about topology.
Yeah, but
in principle, it would be interesting to understand if the topology influence, but here it's not. For Fisher metrics, it's not essential. But indeed, metrics is quite non-trivial. It expressed in terms of
Bessel functions.
Bessel
Yes.
functions, and
yeah, but But if the metric is known, I mean, computing Riemann tensor is just a straightforward exercise. You don't need to do anything else. You just compute by standard.
Yes, I understand that it's simple, but I don't do it. I forget to do it.
I mean, the condition of vanishing of.
I have checked that the apparent manifold will be alpha flat for alpha is equals to plus minus 1. I have checked it. So I have computed the connections, and I have computed the object T, and I have shown that alpha connections goes to 0 for alpha equals to plus minus 1. So in some sense, I have checked that.
In that case, if your connection coefficients are 0, then of course Riemann tensor is 0 as well. I mean, this condition of vanishing of Riemann tensor, I don't know, it reminds a bit the condition that like the vanishing of the beta function for sigma models, but it has nothing to, I mean, it's just.
To be honest, I do not understand properly the feature of alpha flat manifolds. I have read a lot of papers. I have tried to understand it, but at this moment, I do not understand properly what is the main feature of alpha flat manifold. I can see that this is alpha flat. It is not alpha flat, but I do not understand what can I do? What can I do with this?
You know, any group manifold can be made alpha flat. This is called Verzumina-Witten models. In that case, there exists a connection such that any group manifold is flat in that sense.
Yeah, actually, your analogy is correct. So it, to some extent, if you would like to consider to generalize it to the field theory, maybe your remark concerning the beta function could be relevant, but it's an open question.
I mean, in general, the fact that Riemann tensor vanishes implies that the beta function is identically 0 at any loop. So basically, exactly vanishing.
Let me comment this slide. It is for me, it is quite important. If I compute the three indices tensor T, if I compute this object for rapid Cauchy distribution or for simple Cauchy distribution, I can see that this object T is identically 0. So I can't pick any value of alpha. T is identically 0. I cannot pick any value of alpha in order to make my statistical manifold alpha flat. But in case for Gaussian distribution, the object T is not equal to 0. But the metric for Gaussian distribution and for Cauchy distribution are quite similar. They both seem like hyperbolic space. So Cauchy distribution is actually hyperbolic space. The Gaussian distribution seems like stretched hyperbolic space. So for me, there are several open questions, and if you are interested, we can discuss it.
Okay. Other questions?
Any questions?